So today we're going to see how the Laplace transform can be applied to solve a second order linear differential equation with constant coefficients where the forcing function f of t is piecewise continuous. So it can have a certain number of jump discontinuities. And let us recall, if you have a function f of t, its Laplace transform is a function of s, and this is the Laplace transform of f. And the standard notation is to write the function whose Laplace transform we're taking as a lowercase letter f, or whatever the letter might be, and its Laplace transform, the function of s, with a capital letter. And what makes the Laplace transform extremely useful for differential equations is the following. This is theorem 8.3.1. If you have a continuous function for t greater than or equal to 0 and of exponential order s naught, that means it doesn't grow faster than e to the s naught, then the Laplace transform of the derivative f prime, that's the integral from 0 to infinity e to the minus st f of t dt, is equal to s times the Laplace transform of f minus the value of the function at 0. And if we iterate this to calculate the Laplace transform of the second derivative of f, we get that the Laplace transform of the second derivative of f, there should be an f prime there, is equal to, well, the definition, of course, is this. And this is equal to s squared times the Laplace transform of f minus the value of the function's derivative at 0 minus s times the value of the function at 0. And as an example of how one might use this to solve a differential equation, let's take the following. Suppose we have the differential equation y double prime plus y equals 1 with the initial conditions that y of 0 equals 2 and y prime of 0 is minus 1. So if we take the Laplace transform of the left-hand side, the Laplace transform is linear, so that's the Laplace transform of y double prime plus the Laplace transform of y. That's equal to what? It's equal to, and let's say we let capital Y of s be the Laplace transform of our solution y of the differential equation. This is s squared capital Y of s minus the value of the derivative at 0, which is minus 1, minus s times the value of the function at 0, which is 2. So that's the Laplace transform of y double prime plus the Laplace transform of y plus y of s. And this is equal to the Laplace transform of 1. And we know what the Laplace transform of 1 is. And if you don't remember, there is always the table of Laplace transforms at the end of chapter 8. The Laplace transform of 1 is 1 over s. And you don't have to guess or try to remember, look it up. There's no excuse not to get this right. So this is equal to 1 over s. So what this says is we have s squared y of s plus y of s, so that's s squared plus 1 y of s. This is plus 1 minus 2s equals 1 over s. So let me write that down again. So we had s squared plus 1 y of s plus 1 minus 2s equals 1 over s. So we can solve for y of s. S squared plus 1 y of s is equal to, bring this over to the other side, 2s minus 1 plus 1 over s. So y of s is equal to 1 over s squared plus 1 times 2s minus 1 plus 1 over s. Let me write this as, let's say, 2s minus 1 over s squared plus 1 over s times s squared plus 1. So our unknown function y has a Laplace transform equal to this. So we want to find the inverse Laplace transform. Let me just expand this slightly. This is equal to 2 s over s squared plus 1 minus 1 over s squared plus 1. And s over s squared plus 1, if I write that as it's the sum of partial fractions, let's see, what do I know? I know that, let me do that over here. 1 over s times s squared plus 1 is going to be the form a over s plus bs plus c over s squared plus 1. That's what our theorem about partial fractions from first year calculus tells us. This is equal to, so for example, if I multiply through by s, I get 1 over s squared plus 1 equals a plus bs plus c times s over s squared plus 1. Just multiply through by s. And now if I let s equal 0, I get a equals 1. If I multiply through by, well, let me just clear the denominators. That's maybe the easiest thing. Just multiply through by s squared plus 1. I get 1 is a times s squared plus 1 plus bs plus c times s. I hope this is correct. This is a plus b s squared plus, because I have bs squared and a, so I have a plus bs squared. I have a plus a, and I have plus c times s. And I know a is equal to 1, so b plus 1 s squared plus cs equals 0. So if this is going to be 0, these coefficients have to be 0. C is 0, and b is equal to minus 1. So if I did this correctly, I'll check in a second, this is equal to 1 over s minus s over s squared plus 1. This is s squared plus 1. Yep, that's exactly right. And 2s minus s, that's 1. So this is equal to, so y of s equals s over s squared plus 1 minus 1 over s squared plus 1 plus 1 over s. So the Laplace transform of y is equal to this. So y of t is the inverse Laplace transform of y of s. What is the inverse Laplace transform of s over s squared plus 1? Again, we look at our table. For s over s squared plus 1, let's let omega equal 1. That's cosine of t. What's the inverse Laplace transform of 1 over s squared plus 1? If you let omega equal 1, 1 over s squared plus 1 is sine t. minus sine t. The inverse Laplace transform of 1 over s is 1. So that's the solution of our differential equation using the Laplace transform. Okay. Any questions about how we did that? So this is a basic exercise or application of the Laplace transform for solving a differential equation.
Yes, I was wondering if when we reach the stage that we have to look up for the formula, would we have the sheet?
On the exam, I will distribute the sheet, yes.
Okay.
Yeah. So on the final exam, you will have, I will give you this sheet, both sides. So you'll have that as part of your exam booklet.
Okay.
Okay. Now, the more interesting situation is when, so in this case, let me just go back. What was the differential equation we were solving? The differential equation that we started with was y double prime plus y equals 1. So my forcing function, f of t, is just the constant function 1 in this case. That's the right-hand side of this equation. And this is continuous on the whole interval from 0 to infinity. But very often in physical situations, one has a differential equation of the second order with constant coefficients, but the right-hand side is only piecewise continuous. It's not continuous. And the question becomes, how do you solve the equation in that case? And in that case, what we do is introduce the unit function, which is denoted by u of t. So we have the unit step function, u of t, which is defined to be 1 for t greater than or equal to 0, and 0 for t less than 0. So on the number line, the graph of the function looks like this. It's 0, and then just when it gets to 0, it jumps up 1 unit to 1. And more often, one has a shifted unit function, u of t minus tau. So this is equal to what? It's equal to 1 if t minus tau is greater than or equal to 0, and 0 if t minus tau is less than 0, which is the same as saying this is 1 if t is greater than or equal to tau, and 0 if t is less than tau. So for example, if we have the function u of t minus 2, this is the unit function translated 2 units to the right. So it's 0 up until you get to 2, and at 2, it jumps to 1. The value of 2 is 1, and then it's 1 for t greater than or equal to 2. So we have this translated or shifted unit function. And the theorem that describes what happens if you take a function g of t and multiply it by a translated unit function u of t minus tau, this is exactly e to the minus s tau times the Laplace transform of g of t plus tau. Or equivalently, if you take the Laplace transform of u of t minus tau, g of t minus tau, this is just replacing t with t minus tau here, that's e to the minus s tau, Laplace transform of g of t. So this was a calculation. This was theorem 8.4.1 that we did last week. So now I want to consider a differential equation where the forcing function is piecewise continuous. That means it has a one or more jump discontinuities. So let me take the first example, which is done very carefully in the text. We have the differential equation y double prime plus y equals f of t. And we have an initial condition that y of 0 is 2 and y prime of 0 is minus 1. And f of t, this forcing function, is equal to 1 for t between 0 and less than pi over 2. And at pi over 2, it jumps to minus 1, t greater than or equal to pi over 2. So if we wanted to graph this function, for t between 0 and pi over 2, the function looks like this. It's 0, it's 1 at 0, and then it's 1 until it gets to pi over 2. But at pi over 2, it jumps, in this case, it jumps down to minus 1, and then it's minus 1 thereafter. So this is the graph of the function f of t, and you see there is a jump discontinuity at t equal to pi over 2. So how do we solve this differential equation? We write, first of all, the right-hand side, the forcing function, in terms of the unit step function. So suppose we let f0 of t equal the constant function 1, and f1 of t be the constant function minus 1. Then this f of t I can write like this. It's equal to f0 of t plus, so this is correct for t between 0 and pi over 2. And then after pi over 2, it becomes f1 of t. So that's, I can write this as u of t minus pi over 2, f0 of t plus f1 of t. Now, again, what does this mean? So this is equal to, for t less than or equal to pi over 2, for t less than pi over 2, t minus pi over 2 is less than 0. This is 0. So this is just f0 of t. And for t greater than or equal to pi over 2, this is 1. Oops, this should be f1 minus f0. This is 1. And when this is 1, I have f0 plus f1 minus f0. The f0s cancel. This is f1 of t. So in general, this is how you write a function with one discontinuity, a jump discontinuity, in terms of, as one simple equation involving the unit step function translated. So f0 of t, this is 1, plus u of t minus pi over 2. f1 of t is minus 1, that's minus 2. So this is minus 2. So this function f of t with this jump discontinuity can be written like this. So now let's try to solve at least our differential equation. What is the differential equation? The differential equation was y double prime plus y equals f of t, and f of t is 1 minus 2 times u of t minus pi over 2, with the initial condition that y of 0 is 2 and y prime of 0 is minus 1. So let me take the Laplace transform of y double prime plus y. Again, this is the Laplace transform of y double prime plus the Laplace transform of y. That's s squared capital Y of s. Capital Y of s is the Laplace transform of y. So s squared y of s minus f prime of 0 minus s f of 0 plus y of s. So again, this left-hand side is exactly the equation we looked at the very beginning. So we get s squared plus 1 y of s minus f prime of 0. F prime of 0 is minus 1. So plus 1 minus s times 1. And this is going to equal the Laplace transform of 1 minus 2 times u of t minus pi over 2, which is, by the linearity of the Laplace transform of 1 minus 2 times the Laplace transform of u of t minus pi over 2. And the Laplace transform of 1 is 1 over s. Minus 2 times the Laplace transform of u minus u of t minus pi over 2. And what is the Laplace transform of this unit step function translated? So let's just recall that our theorem that I recalled, the Laplace transform of u of t minus tau times g of t is e to the minus s tau times the Laplace transform of g translated. So this is equal to 1 over s minus 2, and this is e to the minus tau is pi over 2, pi over 2s times the Laplace transform of 1, which is 1 over s. So this is 1 over s minus 2 e to the minus pi over 2s times 1 over s. So this is equal to, put everything over a common denominator, 1 minus 2 e to the minus pi over 2s over s. Let me just go back. I think I dropped a term. So again, here is the Laplace transform of the left-hand side of our differential equation. It's equal to s squared plus 1 y of s plus 1 minus s. And that's equal to the right-hand side, which is this. So this equals this, which means that s squared plus 1 y of s, I bring this over to the other side, is equal to s minus 1 did I lose it too? 2 s minus 1 plus this 1 minus 2 e to the minus pi over 2s over s. And let me just double check one thing. Ah, yes. This is s f of naught. F of 0 is 2, so this should be a minus 2s. Good. So s squared plus 1 y of s is equal to this, which means y of s, the inverse, the Laplace transform of my solution is 2s minus 1 over s squared plus 1 plus one minus 2 e to the minus pi over 2s over s times s squared plus 1. Okay. And a few minutes ago, when I was solving the differential equation that I started the talk with, I was able to write 1 over s times s squared plus 1 as partial fractions, so I don't have to calculate it again. This is 1 over s minus s over s squared plus 1. So, what do we have? Let me just write this down again so I can have a clean piece of paper. So whatever is the solution of my differential equation, its Laplace transform, capital Y of s, is equal to 2s minus 1 over s squared plus 1 plus 1 over s times s squared plus 1 minus 2 e to the minus pi over 2s over s times s squared plus 1. And I want to compute the inverse Laplace transform of y. That's my solution y of t of the differential equation. Now, okay, so this I already did. Let me go back and find it in my notes, whatever we just did. Oh, let me just do it. I'll just do it. This is 2s over s squared plus 1 minus 1 over s squared plus 1 plus 1 over s times s squared plus 1 minus 2 e to the minus pi over 2s over s times s squared plus 1. So the inverse Laplace transform, y of t, which is the inverse Laplace transform of y, is what? The inverse Laplace transform of 2s over s squared plus 1. Again, we looked at our table a moment ago for s over s squared plus 1. That's the cosine. That's 2 times the cosine of t. For 1 over s squared plus 1, that's the sine of t. For s over s squared plus 1, when I wrote that as partial fractions, I got here it was, 1 over s minus 1 over s squared plus 1. The inverse Laplace transform of 1 over s minus s over s squared plus 1 is 1 minus cosine t. So this is plus 1 minus cosine t. And then I have to worry about this. Minus 2 times the inverse Laplace transform of e to the minus pi over 2s over s times s squared plus 1. Here we have cosine t minus sine t plus 1. But what is that? Right? That's what we have to figure out. Well, we did have an expression of something that looked like that. Suppose we let, by the way, I'm trying to do this example because this is exactly the first example in, what section are we in? Section 8.5. So I want to compute the inverse Laplace transform of e to the minus pi over 2s over s times s squared plus 1. So suppose I let capital G of s be equal to 1 over s times s squared plus 1. Right. Well, I just calculated what that is, what the inverse Laplace transform is. So the inverse Laplace transform of 1 over s times s squared plus 1, when I wrote it as partial fractions, that's 1 minus cosine t. And what was the theorem we started with about the inverse Laplace transform of a translate of a function? So this was theorem 8.4.1. I will recall it is the Laplace transform of u of t minus tau, g of t minus tau, is equal to e to the minus s tau, the Laplace transform of g of t. Now, what I have here is e to the minus pi over 2s. So suppose I let tau equal to pi over 2. This says the Laplace transform of u of t minus pi over 2 is g of t minus pi over 2. I have e to the minus s pi over 2, Laplace transform of g. That's 1 minus, that's 1 over s times s squared plus 1. If capital G, if we take g of t to be 1 minus cosine t, its Laplace transform is 1 over s times s squared plus 1. So this function, e to the minus pi over 2 times g of s, which is e to the minus pi over 2s over s times s squared plus 1. The inverse Laplace transform is equal to u of t minus pi over 2, g of t minus pi over 2, g of t, 1 minus cosine. Oops, sorry. 1 over s is 1 minus sine t. 1 minus sine t. So this goes in here, and lo and behold, miracles happen. And So we had to solve the differential equation. Y double prime plus y equals f of t, where f of t was a function with a jump discontinuity. It was equal to, let me find where that I was. It was equal to 1 for t between 0 and pi over 2, and minus 1 for t greater than or equal to pi over 2. And our solution is y of t equals cosine t minus sine t plus 1, 1 plus cosine t minus sine t plus minus 2 u of t minus pi over 2 times 1 minus sine t. So that is supposed to be the solution of our differential equation. Well, let's actually check, right? Because you don't know it's right unless you check, and hope it's right. Now you'll notice this function, the solution has a jump discontinuity. This is continuous from 0 to pi over 2, and it's continuous from pi over 2 to infinity, but it's not continuous at pi over 2. There is a jump discontinuity here, right? So for 0 less than or equal to t less than pi over 2, y of t is equal to 1 plus cosine t minus sine t, and this is 0, just equal to this. So if that's y of t, and you'll notice y of 0 is and we had for our differential equation, we had the initial condition that y of 0 was minus 1 and y prime of 0 was equal to 2. So if you let t equal to 0, I get 2. That's not what I want. Oh, no, yeah, y, sorry. In this problem, y of 0 was equal to 2, and y prime of 0 was minus 1. Perfect. Because y of 0 is 1 plus 1 minus 0 is 2. Y prime of t is minus sine t plus cosine t. So y prime of 0 is 0 plus 1 is, minus, is 0 minus 1 is minus 1. So the initial conditions are satisfied. And y double prime of t is minus cosine t plus sine t. So y double prime plus y, when I add these together, I get 1, which is exactly what I'm supposed to get for t between 0 and pi over 2. So that half of the solution works. And what about for t greater than or equal to pi over 2? When t is greater than or equal to pi over 2, this is 1. So my function y of t is equal to 1 plus cosine t minus sine t minus 2 times 1 times 1 minus sine t. So I have 1 minus 2 is minus 1 plus cosine t minus sine t plus 2 sine t is plus sine t. And y prime of t is equal, therefore, to minus sine t plus cosine t. And y double prime of t is equal to minus cosine t minus sine t. So if I take this and add it to this, I get y double prime plus y equals minus 1. And that's what f of t is for t greater than or equal to pi over 2. So everything checks. So I don't want to claim this is easy. It actually is quite difficult when you are trying to master these techniques. But this is a very beautiful and useful method for solving differential equations. And I will do one more example. And again, I'll pick an example from the books, so you don't have to deal with my bad handwriting. Plus, you can study in the book or follow along in the book as you like. So let's see where we are. So the next example is very similar, at least superficially. And let's take a look at it. So this is going to be example 8.5.3. So we want to solve the initial value problem, y double prime minus y equals f of t, with the initial conditions that y of 0 equals minus 1 and y prime of 0 equals 2. And my function f of t, my forcing function, f of t, is defined to be t for t between 0 and 1, and 1 for t greater than or equal to 1. So what does the graph of this forcing function look like? From 0 to t is equal to t, and from 0 to 1 is equal to t, and then it's the constant function 1. So this function goes up and then is horizontal line. So this function is actually continuous, but it's not differentiable at this point. Now, if we wanted to write the function f as one expression, f of t would be equal to t from 0 to 1 plus u of t minus 1. So once t is greater than or equal to 1, this is 1, and I want to make this 1 minus t. Or if you want to have this as a plus t, this is t minus u of t minus 1, t minus 1. This is the same thing. And what is the Laplace transform of f? This is the Laplace transform of t minus the Laplace transform of u of t minus 1, t minus 1. So the Laplace transform of t is 1 over s squared. And the Laplace transform of u of t minus 1 times t minus 1, this is like u of t minus tau, with tau equal to 1. So I get an e to the minus 1 times s, or e to the minus s, times the Laplace transform of t, which is 1 over s squared. So this is the Laplace transform of f. So when we have y double prime minus y equals f of t, Laplace transform of y double prime minus y, this is s squared y of s, minus y prime of 0 minus sy of 0, minus the Laplace transform of y. So this is equal to s squared minus 1, y of s. Y of 0 is minus 1, and y prime of 0 is 2. So this is minus 2 plus s. Sorry, y0 is minus 1. That's why don't I have this looking right? Yes, s squared minus 1 y of s minus y prime of 0 minus 2 plus s. Yeah, all right, that's good, I guess. So, and that's equal to the Laplace transform of f, which is equal to this. So this equals this. So s squared minus 1 y of s, bring everything else over to the other side of the equation. I get 2 minus s, L of f, plus 2 minus s, which is one over s squared plus 1, L of f, plus 2 minus s over s squared minus 1. Sorry. So this equals this, so I'm dividing by s squared. This is my y of s. So I want to find the solution of my differential equation, y of t, has this Laplace transform, capital Y of s. And y of s is equal to 2 minus s over s squared minus 1. I can write this as partial fractions and compute the inverse Laplace transform. And 1 over s squared plus 1, L of f. Which is this. Okay, so let's see how this works out. So I have the Laplace transform of f is equal to 1 over s squared minus e to the minus s over s squared. And or, you know, I'm just going to write this as this is 1 minus e to the minus s over s squared. And y of s is equal to 1 over s squared plus 1 times this, which is two minus s over s squared minus 1 plus 1 minus e to the minus s squared times s squared minus 1. Yeah, okay. So this is correct. And this is exactly so we have to find the inverse Laplace transform of this. So y of t is the inverse Laplace transform of y of s. So I have to take the inverse Laplace transform of this. So let's see. So I'm going to use partial fractions first to solve this. 2 minus s over s squared minus 1 is 2 minus s over s minus 1 s plus 1. So for example, so I can write this as sum a over s minus 1 plus b over s plus 1. Okay. This is just using the elementary theory of partial fractions. S minus 1 over s plus 1. I get two fractions, a over s minus 1, b over s plus 1. So for example, if I multiply this equation by s minus 1, I would get 2 minus s over s plus 1 is a plus b s minus 1 over s plus 1. And if I let s equal to 1, I get 0 here. I get a. When s is equal to 1, I get a is a half. And if I multiply this equation by s minus 1, by s plus 1, I get 2 minus s over s minus 1 is a s plus 1 over s minus 1 plus b. If I let b equal to minus 1, this is 0. I get b is equal to 3 over minus 2. I let b equal to minus 1, I get 3 over minus 2. So so 2 minus s over s squared plus 1 should be equal to this. Let me just check. So if I take a half, 1 over s minus 1, minus 3 halves, 1 over s plus 1. That's, if I put that over a common denominator of s squared minus 1 times 2, I get s plus 1 minus 3 s minus 1. So I get minus 2s plus 4. So I'm not even close. So let me see why my arithmetic isn't right. 2 minus s over s squared plus 1 is going to be a over s minus 1 plus b over s plus 1. So if I multiply by s minus 1 and I let s equal to 1, I get a is equal to a half. If I multiply by s plus 1 and let a equal to minus 1, I get 3 over minus 2. So this should be a half minus 3 halves. So this is s plus 1 minus 3 s minus 1. So that's minus 2s plus 4 over 2 times s squared minus 1, which is, oh, this is right, 2 minus s over s squared minus 1. This is correct. Oh, I solved the problem correctly. I just did the check wrong. So So the inverse Laplace transform of 2 minus s over s squared plus 1 is equal to the inverse Laplace transform of 1/2, 1 over s minus 1, minus 3/2, 1 over s plus 1. Look at our table. The inverse Laplace transform of 1 over s minus a is e to the at, for s bigger than a. So this should be 1/2 e to the t minus 3/2 e to the minus t. And so here's y of s. It involved this term, and this should be the inverse Laplace transform of that, and then this term. So you have to figure out what is the inverse Laplace transform of this. So if I just take 1 over s squared times s squared minus 1, let's see if I can write that as partial fractions. I have 1 over s squared times s squared minus 1. And if I'm lucky, I can write this as, what is that? 1 over s squared minus 1 over s squared minus 1. Or maybe 1 over s squared minus 1 times that. So I get s squared minus s squared minus 1. No. So 1 over s squared times s squared minus 1, I can write like this, which is 1 over s minus 1 s plus 1 minus 1 over s squared. Actually, let me look at my table. Yeah, in my table, b over s squared minus b squared, that is the Laplace transform of the hyperbolic sign of bt. So if b is equal to 1, this is 1 over s squared minus 1. So the inverse Laplace transform, 1 over s squared times s squared minus 1, is the inverse Laplace transform of 1 over s squared minus 1 minus the inverse Laplace transform of 1 over s squared. This is the hyperbolic sign of t, and this is minus t. And if you don't remember or have never seen the hyperbolic sign, sin h of t, this is e to the t minus e to the minus t over 2. But this is a very, it's one of the classical functions. And in fact, I could have made my life slightly easier by writing, I have 2 minus s over s squared minus 1. I worked this out using partial fractions, but I could also do it like this. This is the inverse Laplace transform, 2 times 1 over s squared minus 1, minus the inverse Laplace transform of s over s squared minus 1. Again, I look at my table, and I see that these are the inverse Laplace transforms of the hyperbolic cosine and the hyperbolic sine. So this is 2 times sinh t minus cosh t. The way you pronounce hyperbolic sine is sin-h is sinh, and the way you pronounce the hyperbolic cosine is cosh. So if you put all this together, what do we have? Where was my y of s? So y of s it was 1 minus e to the minus s times 1 over s squared times s squared minus 1 plus 2 minus s over s squared minus 1. So y of t, for 2 minus s over s squared minus 1, that's 2 times the hyperbolic sine sinh t minus cos t plus the inverse Laplace transform of 1 over s squared times s squared minus 1, which is sinh t minus t and then I have this term, e to the minus s times 1 over s squared times s squared minus 1. And I want the inverse Laplace transform of this. But this is just going to be this function, the Laplace transform of this, translated by 0. Just right. So this is times 1, right? So this is like u of t minus 1. This translated by 1. This was sinh ht minus t. So sinh of t minus 1 minus t minus 1, or minus t plus 1. So plus that. So this may be impossible to follow as I'm doing it on a piece of paper and sloppily, but it's done. And I've included every step. In the text, you will find everything legible, but you'll have to insert some of the steps yourself. I have 2 sinh t plus sinh t, so I get 3 sinh or hyperbolic sine of t minus cos t or hyperbolic cosine of t minus u of t minus 1, this is the unit step function, times sinh of t minus 1 minus t plus 1. And that, somewhat miraculously, is the solution of the differential equation. So this is the very last topic that I wanted to cover this semester. So the Laplace transform is very important, and it's also a beautiful piece of mathematical analysis. So in chapter 5, we've learned several things. First of all, the definition of the Laplace transform and how to compute them directly or to look them up in the table. The inverse problem, how to calculate the inverse Laplace transform. How to use that to solve a differential equation with constant coefficients where the right-hand side is a continuous function. And then we introduced the unit step function, and we learned how to solve a differential equation where the forcing function on the right-hand side is not necessarily continuous, but has a finite number, for us mostly just one, jump discontinuity. Okay, so we have 2 more classes after today on Wednesday and next Monday. And I will put together for Wednesday a review sheet for the semester, which means a review sheet for the final exam. And on Wednesday of this week and Monday of next week, I will be going over the review sheet, really, and answering questions.
Professor, are you going to give us any homework for 8.5?
Let me
unit-
just double check my homework sets. Just 1 second. Open. Yes. Yeah, that's almost kind of, yes. I'll do that almost right away. I'll do that this afternoon because I have another class right after this.
Okay.
But I will add some problems in 8.4 and 8.5. So that will be the last official homework. And it also is very much like review for the final exam as well. Thank you for reminding me. Other questions?
No.
If not, then we are
Have a good one, Professor.
done for the day. And I remind you, if you have questions that come up, I have office hours, which are underutilized, but I'm usually available at the times that I put on Blackboard. And but if you have classes or other conflicts with those times, if you send me an email, I can always arrange a time that works for you.
Noted.
Okay.
Okay.
All right. Bye all.
Bye.